Hi, and welcome to Chemical Engineering. My name is Professor Ganesh Sriva. In this presentation, I'm going to talk to you about what is chemical engineering and what do chemical engineers do for a career. So chemical engineering involves chemical process and product design. Not surprisingly, it began as the industrial version of chemistry. It draws heavily from chemistry, math, physics, and biology. And chemies are solving some of the world's most crucial problems. In case you didn't know this factoid, Chemi is one of the highest paying undergraduate majors in the country. This means that when you graduate with a BS degree in chemical engineering, you are currently the second highest in terms of average salary in the nation. So now let's talk about Chemi being a combination of chemical process and product design. For this, we need to know what a chemical product is and what a chemical process is. One of the biggest chemical products that we encounter in our daily lives is fuels. So chemical engineers, as you can see, are heavily involved in supplying energy to a country and to the world. Chemies or chemical engineers are involved in producing commodity chemicals. These are bulk chemicals produced in huge volume. We also are indirect beneficiaries of fertilizers, which are chemicals that enhance the growth of crops and thereby supply us with food, and agrochemicals, which includes pesticides and weedicides that protect the crops by preventing insects and pests from invading them. Then you've got fine chemicals, which are distinguished from the commodity chemicals in that the fine chemicals are produced in lower volumes and lower amounts. So things like thin films, semiconductor chips, etc., which are very important but produced in small volumes, fall into this category. Polymers and plastics probably fall somewhere in between, and they're a separate category by themselves. So polymers and plastics include long chain molecules, molecules which are composed of many repeating units. Then you've got biologics and pharmaceuticals, which is another big category. This includes medicines, vaccines, and drugs in general. Finally, you've got food and consumer products. So that is a snapshot of various kinds of chemical products that a chemical engineer might be engaged in manufacturing. The manufacturing process itself is called a chemical process, and this is how a small portion of a chemical process looks. So typical chemical engineering companies that employ our graduates include fuel companies like ExxonMobil, Shell, and Chevron, chemical product companies like Dow DuPont, Unilever, and then consumer product companies that include Unilever, Procter & Gamble, pharmaceutical companies like Merck, then consulting companies, as well as federal agencies like the Army, Navy, National Institutes of Health, and so forth. So there is a wide demand out there for chemical engineers. Should you earn the degree and do well, there is a tremendous employment opportunity waiting for you. Now we're going to talk about what is chemical engineering exactly. So Chemi began as the industrial version of chemistry, and it draws heavily from chemistry, math, physics, and increasingly biology. So in the next several minutes, we're going to examine this in more detail. So we're going to expand upon the fact that chemical engineering is the industrial version of chemistry. Traditionally, what chemies or chemical engineers have done is they've scaled up lab-scale processes that have been developed by chemists, but scaled them up to an industrial level. So what does this mean? Suppose a chemist comes up with a novel reaction, a novel chemical reaction, A plus B goes to C, where A and B are inexpensive reactants and C is an expensive product. So for example, C could be a plastic, a fuel, a biofuel, for example, a paint, a pharmaceutical, perhaps a COVID-19 vaccine. C could be a cosmetic or a silicon chip. And in all of these cases, it is advantageous and economically beneficial for a company to produce and manufacture and sell large amounts of C. The chemist must have discovered or developed or designed this chemical reaction in a small test tube or a very small volume. And as chemical engineers, we have to discuss and analyze how can we scale this reaction up to a large industrial scale. So that is what typical chemical engineering thinking is all about. So this is a typical final project in chemical engineering design, which is the capstone course taken by undergraduate chemical engineers, where they'll be tasked to take raw materials and make a product but make that product at a certain rate, a certain number of pounds per year. So here's an example of a process design where you've got a reactor, a series of various kinds of separators and pumps and so forth that coordinate in order to give you a chemical process. In CHP 101, we'll begin attacking these kinds of processes to perform simple calculations on them, but as we advance through our curriculum, we're going to examine reactors, separators, and pumps and so forth in greater detail. So I'm just going to focus on 3 of these units: a reactor, a separator, and a pump. Every chemical process typically has a reactor because that's where the chemical reaction takes place. But there's a chemical engineering course that discusses reactor choice for an entire semester. Because in addition to discussing qualitatively, we want to discuss quantitatively using kinetic equations, using the way in which the kinetic equations interact with the physical nature of the process and so forth, to exhaustively discuss reactor type. Then you've got separation analysis. Chemical reactions rarely go unto completion. This is something they don't tell us in high school, but it is true that most chemical reactions are incomplete, and it is necessary to figure out how do you separate the products from the reactants and give pure product to the end user. That brings up a related question of whether we should recycle the reactant back to the front of the reactor at all. So questions like how far will the reaction go are answered in thermodynamics courses. Questions like should we recycle is answered in CHP 101. Questions about how do you separate product are mostly addressed in the separations course. Questions about pump design are addressed in CHP 422, the fluid mechanics course. And various other chemical engineering courses address various aspects of these processes. We also address the overall design, the cost, the startup, whether wastes are going to be formed, and whether the process is safe. So at the end of your chemical engineering career, we hope to make you a competent chemical engineer who can design processes like this and use those talents in the chemical industry. But that is a portion of what you study in chemical engineering. You typically start out by taking several courses in engineering, math, chemistry, and physics. Then the blue courses, the chemical engineering ones, come in. As you advance to the senior year, the junior and senior years, you take more and more chemical engineering classes, and you end up taking electives in the senior year. The electives are areas of frontier areas in chemical engineering that explore where the field is heading now. So many of the chemical engineering classical problems were solved maybe about 10, 20, 30 years ago. They were completely solved, and chemical engineers since then have been using their expertise to solve newer problems at the forefront of the field. That includes developing new batteries, coming up with new biopharmaceuticals and vaccines. It won't be surprising if a vaccine is found for COVID-19 and chemical engineers are heavily involved in either the discovery or the manufacture of the vaccine. Chemies are also involved in catalysis, polymer science, metabolic engineering, protein engineering, and so forth. So this is a sampling of electives offered in the past year that gives you an idea of what electives in this department are like. So we've seen that there's a lot of chemistry, math, and physics in chemical engineering. We're going to briefly examine where the biology is. So it turns out that biology and biochemistry play an increasingly important role in the activities of chemical engineers. Many chemical processes are catalyzed by living organisms. This includes traditional processes such as beer brewing, which is an age-old process, to the making of antibiotics, which is about 100 years old, to the making of insulin, which is about 40 years old. So insulin is a drug that diabetic patients take. Back before 1980, insulin was manufactured by slaughtering pigs and obtaining them from the pig pancreas or porcine pancreas. Today, insulin is obtained by genetically engineering the bacterium E. coli and getting E. coli to make the human insulin for us. This was pioneered by a company called Eli Lilly in Indianapolis, and now it's become a worldwide process. chemical engineers are also working on making things like future fuels, biofuels like ethanol and butanol in genetically engineered bacteria. You must have heard of ethanol being a biofuel, but not a very efficient one. That's because there are disadvantages to using ethanol as a biofuel, but it turns out other molecules like butanol can be much more superior biofuels that can rival gasoline in its properties. So getting bacteria like E. coli to make butanol at sufficient rates to make it economically competitive and sustainable is what some chemies are working on. So these are various different biological and biomolecular areas where you can also be exercising your expertise as a chemie. Here is a snapshot of career paths for chemies. You could get an excellent career in chemie with just a BS degree, but also with an advanced degree, you could get a better job satisfaction and better choices of opportunities in your degree. So for example, if you want to become a technical engineer and stay in that job, a BS degree is wonderful. If you want to if you want to design a chemical process in the industry, if you want to become a lead engineer or scientist, for example, in the chemical or the biotech industry, then an MS or a PhD would be necessary. You can be a patent reviewer with a BS degree, but if you want to become a patent attorney arguing chemical patents in courts, then you need a law degree in addition to the BS degree. So again, if you want to talk to us about what the different career paths are and what are the differences between various degrees, then we'd be happy to talk to you about that at that time. Welcome again to the program, and hopefully you'll have a fantastic ride through it.